What are the finite differences? These are commonly used to approximate derivatives of a function using discrete points. There are three basic types of finite difference formulas. We have the forward difference, the backward difference, and the central difference. Let's look at each. Let's look at the forward difference. The forward difference approximates the derivative of a function at a point by using the next point in the sequence. So we are saying we are approximating the derivative of a function. So f prime of x approximates to f of x plus h minus f of x everything divided by h. And h is what we are calling the step size. Okay, so if h is the step size, let's look at an example. Let's approximate the derivative of a function f of x is equal to x squared at x is equal to 1 with a step size of 0.1. So we need to look for f of 1 plus h. So this is f of 1 plus h, which is 1 plus 0.1, and that is 1.1. So what will that be? We substitute it in the value of, we substitute 1.1 in f of x, where x is. So we shall have f of 1 plus h equal to 1.1 squared, and we get 1.21. What about f of 1? F of 1 will obviously give you 1 squared, and that is equal to 1. So we shall find that f of x, we said, which is equal to f of x plus h minus f of x, we divide it by h, which is the step size. And this is going to be, we said f of x plus h is equal to 1.21 minus f of x, whereby x is equal to 1, okay? And we got that f of 1 as 1, divided by the step size, which step size is equal to 0.1. So we'll be able to get 2.1, and that means that the approximate value of f of x at x is equal to 1 is 2.1. If I differentiate f of x, you have f of x equals x squared. Now, if I differentiate this and I'm using the exact derivative, f of x prime, or the first derivative of f of x, is going to be 2x. So if I put in my value of x is equal to 1, then obviously f of f prime, or the first derivative of f of x at x is equal to 1, is going to be 2 times 1, and this is equal to 2. But the approximate value is telling us it is 2.1. So it is still approximately equal to 2, because the 0.1 is not so significant in some instances, though it can, of course, be a huge error when it comes to some applications like electronics. If you are talking about this being, for example, milliamps, if you want only 2 milliamps and you send 2 milliamps, this can have a devastating effect on devices. So it is very important to know that these are approximations, and somewhere they can apply, and in other areas they may not apply. So this is the forward difference. We are looking at finite differences. So we have finished with the forward difference. So let's look at the backward let's look at the backward difference. So the backward difference uses a previous point. The other side, we said it uses the next point in sequence. The backward difference uses the previous point in the sequence to approximate the derivative. So we are saying f prime of x is approximately equal to f of x minus f of x minus h, everything divided by h. So what is x minus h? It will be the value of x minus the step size. So if we use the same example, f of x is equal to x squared and h is equal to 0.1, we approximate the derivative of this function x is equal f of x is equal to x squared at x is equal to 1. That means we need to look for f of 1 minus h. And the 1 minus h is 1 minus 0.1, which gives you 0.9. So we look for f of 0.9. And f of 0.9 is equal to 0.9 squared. Because in the place of x, we have 0.9. Remember, it is squared, so we get 0.81. So when you get 0.81, that is f of 1, I mean x minus h. Then we look for f of x. Remember, x is equal to 1, so we are looking for f of 1. So f of 1 is equal to 1 squared, and we are getting 1 also. So we substitute in this formula, then what we shall get is 1.9. So we see that the exact derivative is 2, but the backward difference gives an approximation of 1.9. Likewise, I said this kind of approximation can work in some areas, and in other areas it may not work. This can work maybe in mechanical, but in electronics it may not work. Okay, so you must understand where some of these methods can be applicable. Then it still remains an approximation because 2 and 1.9 are very close to each other. Then we look at the central difference, which is the most commonly used one. The central difference formula uses both the next and the previous points in sequence to approximate the derivative, making it more accurate than the forward or backward differences. So this one has fx plus h, has fx minus h, and divided by 2h. So using the same example, let's look for f of x plus h. We already said this is the same as f 1.1, and we said this is 1.21. Then f of x minus h, we said this is the same as f of 0.9, and we said this is the same as 0.81 because this is x squared. So here is x squared, and this is 0.9 squared. This is 1.1 squared, so giving you 1.21. What about h? H is 0.1. So what do? We just substitute in the formula for central difference method. So f of 1 will be approximately equal to 1.21 minus 0.81. We divide it by 2 times 0.1. And if you put it on the calculator, we have 1.21 minus 0.81. We divide it by 0.2. And this gives you exactly 2. So the approximation gives you 2. So you can see that the central difference method is more accurate than the rest because it gives you the exact value, or the value which is equivalent to the exact derivative. So that's what we have. and therefore you can see those three values and which one. You remember the exact one, exact value is 2. So you see it is equivalent to that, and therefore the central difference method gives a better approximation.